Hello friends, welcome back to the lecture series on engineering mathematics. In previous video, we have seen periodic functions, even and odd functions, and their algebraic as well as integral properties. To revise those concepts, please refer the part 1 on Fourier series, where link is given in the description. Now, in this session, we are going to discuss about the Dirichlet's conditions and the Fourier series representation of the given periodic function. So, let's start with the Dirichlet's conditions. If f of x is defined in bounded interval, say c to c plus 2l, satisfying some conditions, which is f of x is finite and single valued, and also it is integrable in the given bounded interval. Second condition is f of x must have finite number of discontinuities in the interval. Remember, those discontinuities should not be infinite discontinuities. Third condition is f of x must have at most finite number of maxima and minima in the given bounded interval. Let's take one example. If f of x is equal to tan x, where x lies in the interval 0 to 2 pi. So whether it satisfies Dirichlet's condition or not, let's check. So first, for this f of x is equal to tan x, here if you substitute any value within this interval 0 to 2 pi, suppose if we put x is equal to pi by 2, then at this point your function is not finite. So condition number 1 is not satisfied by f of x. So tan x does not satisfy Dirichlet condition since f of x tends to infinity as x is equal to pi by 2. Let us consider another example. If we consider f of x is equal to sine inverse x in any interval, then it has not single valued function. Same is the case with any algebraic function of the form 1 upon x minus a in the interval 0 to twice a. It does not satisfy Dirichlet condition because your function is infinite discontinuous at x is equal to a. And moreover, if we consider another example, suppose f of x is equal to e raised to ax, where x lies in any real interval, then this function satisfies all the Dirichlet's conditions. So let's discuss the Fourier series. Fourier series is nothing but synthesis of periodic function. Before going to discuss the formula for Fourier series, remember Fourier series is calculated for periodic functions only. Fourier series of periodic function is composed of harmonically related sinusoids combined by the series. These are some remarks required before calculating the Fourier series. Now, we discuss about the formulation. We consider f of x is periodic function with period 2l defined in the bounded interval say c to c plus 2l, where length of the interval is twice l, where c is any finite number. And this periodic function f of x also satisfy the Dirichlet's conditions in the given interval c to c plus 2l. Then the Euler's representation for a Fourier series is given by f of x is equal to a0 upon 2 plus summation n varying from 1 to infinity an into cos n pi x upon l plus bn into sine n pi x upon l. If you observe, since f of x is periodic function with period 2l, we know that cos is periodic function with period 2 pi and the general period is 2n pi. If you divide it by the constant term, that is n pi by l, if you simplify this, we get this is periodic function of period twice l. Same is the case with sine n pi x upon L is periodic function with period twice L. So conclusion is, if f of x is periodic function with period 2L, then we can represent this f of x in terms of series of periodic function with the same period, where a0, an, bn are known as Fourier coefficients. And to evaluate those Fourier coefficients, the Euler's formula is given by 1 upon L integration of f of x with respect to x in the interval c to c plus 2L. An is given by 1 upon L integration from c to c plus 2L of f of x into cos n pi x upon L with respect to x, and bn is given by 1 upon L integration from c to c plus 2L of function f of x into sine n pi x upon L. So a0 is the constant term or the first term in the Fourier series. An is the coefficients in the Fourier series of cos n pi x upon L, where n varies from 1 to infinity. And bn is coefficient of sine n pi x upon L. So we use cos as well as sine while calculating an and bn. So depending upon different cases for c and L, we can generalize these results. So we consider case 1. If f of x is periodic function in the interval 0 to 2 times pi. If you compare, we take c is equal to 0 and L is equal to pi. Then your Fourier series representation will be f of x is equal to a0 upon 2 plus summation n varies from 1 to infinity an, where an is coefficient of cos n pi x upon L. So since value of L is equal to pi, so we can simplify it here, and we are taking the term cos nx only, plus bn times sine nx. So this is your Fourier series representation for periodic function f of x with period 2 pi in the interval 0 to 2 pi, where we can generalize the Fourier coefficients as well. a0 is equal to 1 upon pi integration from 0 to 2 pi of the function f of x with respect to x. An can be calculated by 1 upon pi integration 0 to 2 pi f of x. Since an is coefficient of cos nx, we take cos nx here while calculating Fourier coefficient an. Similarly, bn can be evaluated by using formula 1 upon pi integration 0 to 2 pi of the function f of x into sine nx with respect to x. So depending upon your function f of x, we can evaluate these three definite integrations, substitute those values, and we get the required Fourier series for the function f of x. Now we consider case 2. If f of x is periodic function defined in the interval minus pi to pi. So again, if you consider this interval, the lower limit is minus pi, upper limit is pi, in the middle we get 0. So for this type of interval, we need to test whether this f of x is even function or odd function. So if f of x is even, the nature of Fourier series will be different, and if f of x is odd function, then nature of Fourier series will be different. How? Let's discuss. So first, if we consider f of x is neither even nor odd function in this interval minus pi to pi, means we cannot conclude whether we replace x by minus x, then we get function f of x as it is. If f of minus x is f of x, then your function is even function, and we apply the integral properties of even function while calculating Fourier coefficients. If f of x is odd function, then f of minus x will be negative times f of x. In that case, Fourier coefficient in this range may or may not be 0. So depending upon the case, we start with neither even nor odd function in the range minus pi to pi. If f of x is neither even nor odd function in this range minus pi to pi. So instead of pi, you can consider any general period, that is L. Then the given Fourier series will be f of x is equal to a0 upon 2 plus summation n varying from 1 to infinity an into cos nx plus bn into sin nx, where the Fourier coefficients in the range minus pi to pi is calculated by using formula a0 is equal to 1 upon pi integration minus pi to pi f of x into dx. An is evaluated by 1 upon pi integration from minus pi to pi f of x cos nx with respect to x. Similarly, bn can be evaluated by the formula 1 upon pi integration minus pi to pi f of x into sin nx dx. This is your case when the interval is minus pi to pi and f of x is neither even nor odd function. Then remember these formulas. Now we move to the next case. If f of x is even function in the range minus pi to pi, then so you can consider any case for even function, whether it is interval minus pi to pi or 0 to 2 pi as well. If f of x is completely trigonometric function, then we can test the even as well as odd properties in the range 0 to 2 pi as well. So if f of x is even function, then the corresponding Fourier coefficients will be a0 is evaluated by 1 upon pi integration minus pi to pi f of x. This was the initial formula that we start with. Since f of x is even function, then by using integral properties of even function, we can rewrite this integral as 2 times integration 0 to pi f of x dx. Similarly, an can be calculated by using formula 1 upon pi integration from the initial interval minus pi to pi f of x into cos nx with respect to x. Since f of x is even function of x, cos is also even function of x, product of two even function is always even, then we can rewrite integration of even function in the range minus pi to pi as 2 times integration 0 to pi. So this will be your formula for Fourier coefficient an. While calculating bn, we start with formula 1 upon pi integration minus pi to pi f of x into sin nx with respect to x. Since f of x is even function, sin nx is odd function, product of one odd and one even function is always odd, and integration of the form minus pi to pi is equal to 0. So you can mention, since f of x multiplied by sine nx is an odd function, therefore we got the Fourier coefficient as a0 and an only. Here bn vanished. Therefore required Fourier series is nothing but f of x is equal to a0 upon 2 plus summation n varies from 1 to infinity an into cos nx. Since bn is equal to 0, so there are no terms containing sin nx. So this will be the Fourier series representation for even function. We also call it as Fourier cosine series for periodic function f of x with period 2 pi in the interval minus pi to pi, provided that f of x is even function in that interval. Now we move to the next case, case 3. If f of x is an odd function in the interval minus pi to pi, then we start with Fourier coefficients again. Formula for a0 is 1 upon pi integration minus pi to pi f of x into dx. Since this f of x is odd function, then by using integral properties of odd function, we get a0 is equal to 0. Similarly, an can be calculated by using formula 1 upon pi integration minus pi to pi f of x into cos nx dx. Now, since f of x is odd function, cos nx is even function of x in the interval minus pi to pi, then product of one odd, one even function is always odd. So by using integral properties of odd function, we got an is equal to 0. Now let's check bn. Since bn is calculated by using formula integration minus pi to pi, we have taken 1 upon pi outside the sign of integral. F of x is multiplied by sin nx dx. Since f of x is odd function, sin nx is also odd function, product of two odd function is always even, and integral property of even function is we consider half the range and take twice the integration. So it is 2 upon pi integration 0 to pi f of x into sin nx dx. This is your formula for bn. Since a0 and an are vanished for the given odd function, then the corresponding Fourier series can be represented as, therefore f of x is equal to a0 gone, an gone. Now the remaining term is summation n varies from 1 to infinity bn into sin nx. This is the required Fourier series for the given odd function. We can call it as Fourier sine series of given periodic function f of x in the range minus pi to pi. So remember, Fourier series of odd function in the range minus pi to pi is always Fourier sine series, whereas Fourier series of even function in the range minus pi to pi is always known as Fourier cosine series. In Fourier cosine series, terms of bn will be 0, and in Fourier sine series, a0 as well as an is equal to 0. For the derivation of Fourier series as well as Fourier coefficients, students can refer the Ordinary Differential Equations book by M.D. Raisinghania, chapter number 6, topic number 6.2 for the reference and derivations. I hope you have understood this. In next session, we are going to refer some ready reference formulas for evaluating Fourier series of the given periodic function.